Let's look at a pulley example again and show that energy is conserved even when the pulley now has mass. So we are dealing with pulleys that have mass but still frictionless. Once again, this is true for any sort of pulley system that you might imagine. Let's focus on this one for the proof. First thing we're going to do is draw some free body diagrams, and now we will have to draw an extended free body diagram for the pulley additionally. So let's start with the masses. So those are the free body diagrams for the masses. Note that because the pulley is massive, the tension on either side of the pulley isn't necessarily the same anymore. And so we have T1 and T2 to represent those tensions. And here is the extended free body diagram for the pulley. We have forces acting at the axle, the normal force, and the weight of the pulley going down. And then we have the tensions creating torque for the pulley. Without losing any generality, let's assume M2 is bigger than M1 so that the whole system is moving downward, like that. And therefore the pulley is rotating clockwise. All right, let's calculate the work done by tension 1 and see what happens with that. As before, because the whole system is moving as one object, any distance that M1 moves horizontally is the same distance that M2 moves vertically. And so I have labeled that here. Focusing now on mass 1, let's find the work tension does to move mass 1 a distance d. We have the force of tension and the distance. And there we have it. Now let's find the work done by tension 2 on mass 2. There we go. And they don't cancel like they did in the massless pulley case. What's going on? Well, we forgot to take into account the work that the tensions are doing on the pulley itself. It's a rotational work. T1 creates a torque that tries to move the pulley counterclockwise, and T2 creates a torque that tries to move the pulley clockwise. So let's find the rotational work done by these tensions now on the pulley. So here's the work done by tension 1 on the pulley. Note a couple of things. The torque done by tension 1 on the pulley is represented by this T1R term. And then we have the angular displacement theta. However, notice that the torque tries to rotate the pulley counterclockwise, but the pulley is undergoing an angular displacement that is clockwise. So the torque and angular displacement go in opposite directions, and that's why there is a minus sign there. Note also that I have assumed that the pulley has a radius capital R. We can do something similar for the work done by tension 2 on the pulley, and there we have it. This time the torque pushes the pulley in the same direction as the angular displacement, so there is no minus sign. It's a positive amount of work done. The angular displacement in both equations is the same because, once again, this whole system is moving as one system, and the rope that's moving along the pulley is moving along it without slipping. Consider a point on the rim of the pulley representing a piece of the string as the pulley rotates, and you'll see as the pulley rotates, it moves an angular displacement of theta. And so that angular displacement is just one angular displacement. It's the same displacement for both tensions. But now, how can we relate these angular displacements to other quantities that we know in the problem? Because right now it's looking like things aren't going to quite cancel. Well, the answer is in the figure that I just drew. What is the distance between these two red points on the rim of the wheel? The answer is D. Because this whole system is moving as one system, the rope is moving along the edge of the pulley without slipping, and so the distance that mass 1 moves has to also be the distance that the point at the edge of the pulley moves in order for there to be the same amount of rope on the other end of the pulley for mass 2 to also move a distance d downward. Knowing that, we can calculate what the angle theta is in terms of d. We know that the arc length formula gives us S equals r theta. S, in this case, the arc length is d. And then we can solve for theta and plug it into our equation for work. And then you'll see the radius cancels out. And so you'll see that the net work done when we add it up does indeed cancel out. And so we get that energy is conserved because the work done by the non-conservative forces is 0. We also have the normal force, of course, for block 1, but that does no work because it's perpendicular to the path. And then we have the normal force from the axle on the pulley, but that does no torque, and it also does no work because the pulley has no translational motion. And it does no torque because we can take the torque, as we did, about the axle. And so no torque from any forces acting at that point. So energy is conserved even when the pulley has mass. And you can see from this argument, and I'll leave it as an exercise for you, it'll be true for any pulley system that you will encounter. So let's now run through an example of using energy conservation to solve a problem with a massive pulley system. All right, so let's consider this classic problem where we have a pulley with mass now, and the system starts at rest. Mass 2 is bigger than mass 1, so it moves to the ground. Mass 1 moves up. And we want to know the velocity of mass 2 just before it hits the ground. Because the whole system is moving together as one object, the speeds are the same for both blocks all throughout, and the angular velocity will be related to these speeds also, as we will see soon. As for the mass of the pulley, that's going to create a moment of inertia. So let's write something down for that. Let's assume that the pulley is a solid disk, and therefore it has a moment of inertia of 1/2 mr squared. We are assuming, of course, that we're taking the moment of inertia about the center of the pulley, and that's what we will be measuring torques with respect to as well, about the center of mass of the pulley. All right then, so as we know, this is a pulley system, energy is conserved. I'll just put the whole pulley system inside my system for ease of drawing. I'm including the earth in the system, the pulley, the 2 blocks, and the ropes. As we know, and I've demonstrated, the work done by the tension forces is 0, and so it doesn't matter if it's inside the system or outside the system, despite being non-conservative. All right then, so let's write our conservation of energy formula. So we have the change in kinetic energy of all the objects in our system, and also the change in potential energy of all the objects in our system. I need to get the kinetic energy change for each object in the system and add them together, and the potential energy change for each object in the system and add them together. So here are the energy terms for the objects in our system. We have a kinetic energy term and a potential energy term for block 1, a kinetic energy term and a potential energy term for block 2, and also a rotational kinetic energy term for the pulley. If the pulley was translating, then we would have a translational kinetic energy term for it as well. That is, if it was rotating as well as translating. If it was just translating, then we would ignore rotational kinetic energy and just have translational. But all the pulley is doing as it is moving is rotating, so it gets a rotational kinetic energy term. Meanwhile, the blocks, they just translate, they don't rotate, they get translational kinetic energy terms. Now that we've written out all the energy terms for the objects in our system, let's plug in the known values. We have plugged in the initial velocities, which we know are 0 for each of our blocks. And the initial angular velocity is 0 for the pulley as well, because the system starts from rest. The final velocity for each of the blocks is the same, which I'm calling V final. The initial height for block 1 is 0, and its final height is h. And then we have the opposite for block 2. Its final height is 0, and its initial height is h. So let's simplify this down. This is what we get. And now count the unknowns, V final and omega final. I don't have either of them. I have 2 unknowns, but just one equation to solve for them. So I need to reduce my unknowns. How can I do that? Consider a point on the edge of the pulley. This point moves as the pulley rotates. At what rate is that point moving? Well, by our previous considerations, we know the point moves a particular distance, and that distance is the same distance as either of the blocks move, and it moves that distance at the same rate of time. Why? Because the rope is moving over the pulley without slipping, and it is moving at the same rate as the blocks are moving. And so the rope is moving over the pulley at the same rate as a point on the edge of the pulley, which is where the rope exists. We therefore can calculate the velocity of a point on the edge of the pulley, which is going to be the same as the velocity of the rope, which is the same as the velocity of the masses, as everything moves together as one object. And as the rope moves without stretching or compressing and moves without slipping over the pulley, we get the speed of a point on the edge of the pulley is equal to the speed of the masses, and that's related to the angular velocity of the pulley and its radius. So now we can use this relationship to rewrite omega final in our energy equation. Note also, before I do that I've already made the substitution for the moment of inertia of the pulley. So omega final is V final over R, which when it gets squared, the R squareds are going to cancel. Watch. We have an R squared on the bottom and R squared on the top. And so we are left with 1/2 mass of the pulley times V final squared. Our conservation of energy equation then becomes, then we can simplify by combining like terms together, and the following expression results. The 1/4 comes from multiplying the 1/2s together. So the 1/2 here and the 1/2 there, if you were wondering where that came from. And now we can solve for final velocity. Just move that term over to the left-hand side and divide by that term. And we get the final velocity. This minus sign is not a mistake. Just bring the minus sign in to the m1 minus m2. And then you'll get negative m1 plus m2, or in other words, m2 minus m1. m2 is bigger than m1, so this is a positive number. We're all set mathematically under the square root. This 2 comes from dividing this term, so you get a 1/2 in the denominator, which can then be put into the numerator, and it becomes a 2 that way. Keep, change, flip. Now that we have the final velocity, we can calculate a numerical value for it by plugging in the various numbers that we have. And now let's grab a calculator out to see what this is. And we get 5.26 meters per second. Note that this is a smaller velocity than what we would have gotten if the pulley was massless. If the pulley was massless, you just plug in the mass equal to 0 in the equation for final velocity that we have over here, and the result is 6.26 meters per second. This makes sense because once the pulley has mass to it, it takes some energy to turn it. So some energy is taken away from the system and put into turning the pulley, which means there's less energy in the kinetic energy of the blocks, resulting in a smaller velocity at the end. Now that we have the final velocity, we can also get the final angular velocity. That is the final angular velocity of the pulley. And there we go. That's the final angular velocity of the pulley. Plugging in the numbers we have, we get 5.26 radians per second. In this case, it's a numerical coincidence that they are the same in number, they're not the same in units, because the radius was 1 meter. But it could have been 2 meters, then this would have been half as much. Just make sure that you're careful with what you're doing and plug in the values that you have. And so we have solved the pulley problem. We have found the final velocity of the block 2 just before it hits the ground, as well as the final velocity of block 1 at that moment in time, and the angular velocity of the pulley at that moment in time. Notice that conservation of energy was significantly easier to use, even though I drew it out some for the purposes of explanation, but it was significantly easier to use than using the Newton's second law method of using torques and angular accelerations and so forth. When might you use one method versus the other? Well, as you can see from energy conservation, you get direct information about the speed and height. So if that's what you're interested in, then energy conservation is a great idea. If, however, you want to know the torques exerted by the ropes or the forces of tension, then you'll need to use a Newton's second law approach. Likewise, if you want a direct calculation of the angular acceleration, or maybe even the moment of inertia, although it does appear in the energy conservation equation too, so it depends on what you're given, then maybe the Newton's second law torque equation is a better idea, because that's a direct way of calculating those quantities. All in all, as usual, choose whatever is practical and makes it easiest to solve for the quantities that you're looking for based on the quantities that you know.